There it goes. Yeah. Okay. All right, so we are talking about 15.1 today, which has to do with what we call energy cycles. And so there's got a lot of definitions up here because in these cycles, there's several different parts. And so a couple of things before we go down to kind of the main area is just that we're going to talk about a lot of these different things. So we're going to talk about enthalpy of hydration, enthalpy of ionization. Oh, why did it just drop out? Like it lost the connection or something. There it goes. Okay, so we're going to talk about enthalpy, or sometimes they use energy of hydration. So that means that something's being hydrated with water. We're going to talk about ionization energy, which is one of our periodic trends that we learned about back in topic 2. We're going to talk about enthalpy of atomization, which is kind of a new term. We're going to talk about electron affinity, which that's not new. That's from topic 2. That's one of our periodic trends. We're going to talk about lattice enthalpy. That's a new term. And then the enthalpy of covalent bonds and solutions. So there's a lot of different terms that are related here. So that's what I'm going to kind of go through today. And then you can watch the other videos that are on Canvas for kind of the rest of the information. And then the second thing is that we have these 3 things: enthalpy of solution, hydration enthalpy, and lattice enthalpy. They're all related in what we call an energy cycle. So we can use like Hess's law to perform calculations with them. So what we're going to be talking about today is how do you create what's called a Born-Haber cycle. And a Born-Haber cycle is this energy cycle that is going to relate all of these different terms to each other. And so we're talking about sort of how does a ionic compound break apart into its elements, or how do the elements form the ionic compound, and kind of what's going on with the energy and the enthalpy in all that process. Okay. So let me scroll down. So the first thing is all these definitions. Okay. And so this first one is lattice enthalpy. And if you notice on the symbol, it still has delta H because it's a change in enthalpy, just like from topic 5. But it has this little 0 up at the top, and then it has a kind of like subscript size. It has LAT. And the LAT just stands for lattice. So when it has that LAT label, they're telling us it's the lattice enthalpy, because there's going to be other ones that we're going to talk about later on down at the bottom. So lattice enthalpy, as it says right here, it can be defined 2 different ways. It can be, and it depends on the direction of your reaction. So in this one, we are starting with the solid ionic compound, and it's being separated into the gaseous ions. So notice that it has to be a solid ionic compound, and it's separated into gaseous ions. The other way is backwards. If I look at the one right below this, the one right below it, this one is a solid ionic compound is formed from the gaseous ions. So if you look at this one, it's backwards. It's just the reverse reaction. Okay. And so the difference here is that one of them's endothermic and one's exothermic. So if you look at this first one's endothermic, and do you remember what endothermic means?
In, like the thing get in?
It's absorbing energy, or it's absorbing heat. And so that means that the delta H is positive. So see how it's got that plus sign right there? The other direction, yes, exothermic, which means the heat's being released, or the energy's being released. And so that one's got the negative sign for the delta H because it's negative. So IB uses this first definition. That's what it says right here. So both definitions are like valid, but the one IB uses on all the questions and all the tests is this first one. Okay. And so that means that lattice enthalpy is endothermic and it has a positive change in enthalpy for IB purposes, okay? The other definitions are going to be important for us to know to create these cycles. So we have the lattice enthalpy, and that's the one we just talked about. So I'm not going to go over that one a second time because it's just the same thing that's right up at the top. One thing I do want to point out is be careful with your state symbols because this ionic compound is solid, but notice that both of your ions, they're gas form, okay? That's very important. You have to include that term, like in the definition. It's, 1 mole of solid ionic compound is separated into gaseous ions. You have to use that term gaseous to describe them. The next definition is enthalpy of atomization. Notice again, it has kind of the delta H symbol, but now it has ATOM down next to it, kind of like the size of a subscript. And so again, that's their way of telling you that's the enthalpy, because delta H just tells me it's an enthalpy. I have to use this sort of label at the end to tell me which one it is. So with their lattice enthalpy was LAT, so the enthalpy of atomization is ATOM. They just use atom to abbreviate it. So this one is the definition. Okay, it says it's the enthalpy change will actually go back and undo that one. And so standard state means like how it naturally occurs. So if we look at the example they give us sodium, and sodium's a metal, so naturally it's a solid. And so what happens is when it's atomized, that means that 1 mole of solid sodium, it's still sodium, but now look, it's a gas. So all we did is basically we did like sublimation. We turned it from a solid to a gas, okay? The one thing again that I want to point out is that this is endothermic. So that one was endothermic. This one is endothermic. And I can tell it's endothermic because right here, the energy or the enthalpy value is positive. Okay, so remember, endothermic is always positive. So those are both positive delta H's. The next one that's important to know is first ionization energy. Now, this one's not a new term. We learned this in topic 2 last year. So now we're kind of applying it to another topic. And so ionization energy, as it says here, it's the minimum energy required to remove 1 mole of electrons from 1 mole of gaseous atoms. And so what you're going to see is these are going to kind of go in a certain order. So right here, we take the element and we turn it from its natural standard state, which for sodium was a solid, we turn it into a gas. Then once it's a gas, then it goes through this ionization energy process, and it goes from the gaseous element to the gaseous ion. We take away one of its electrons. Okay, we remove the electron. And that one also is endothermic. I can see here that it's a positive delta H value, positive enthalpy change. Okay. And then same thing here on the symbol, it's the delta H, the little zero up in the top. And then this one, because it's the ionization energy, they just use a lowercase I to indicate which one it is, that it's the delta H for ionization energy. Okay, then after that, the next one is going to be dealing with our other elements. So that was all to deal with the metal in the ionic compounds. So as you notice, there were sodium in those two. The other ones that are going to be on here are going to have to deal with the non-metal, because remember, in an ionic compound, we always have a metal and a non-metal. So the next one is the bond dissociation enthalpy, and that one's just usually used as a capital E. And this is the enthalpy change when 1 mole of bonds is broken in the gaseous state. And again, this is endothermic. I can see it's got a positive delta H there. And so this one is going to have to deal with the non-metal. So I can see that I have chlorine, diatomic chlorine. That's the natural state of chlorine. It's diatomic and it's in the gas form. And so what this one is doing, when you say you're dissociating a bond, what I'm doing literally is I'm taking my molecule of chlorine that looks like this because it's 2 chlorine atoms that are single bonded together. And what I'm doing is I'm literally breaking the bond between them. and I'm creating 2 individual sodium atoms, like this product side. So when they say bond dissociation enthalpy, that's the enthalpy or the energy that it takes to break the bond in 1 mole of this element. Okay, so it says 1 mole of bonds is broken in the gaseous state. So the only thing that changes here is we went from 1 chlorine molecule to 2 individual chlorine atoms. They're both gas states still. We're just breaking that bond to split them apart. Because if we don't break their bond, we are not going to be able to form our product of sodium chloride. Okay, so we have to break their bond in order to make our new product. So then, after that comes the electron affinity. So the electron affinity, and it's the first electron affinity. Here we have the first ionization energy. I didn't point that out, but sometimes you might have a second ionization energy, and it depends on the element. If I go back up here to the very beginning, it tells us that we need to be able to do these cycles for group 1 and 2 oxides and chlorides. And so group 1 and 2, remember that's like sodium is in group 1, so it's +1, but something like calcium is in group 2, so that's 2+. So any of your group 2 metals, they're going to have 2 ionization energies because they have to lose 2 electrons. So just keep that in mind as well when you're going through these questions. So back to this one. So this is the first electron affinity. So just like with the ionization energy, we could have 2 of these. If our nonmetal can gain 2 electrons, like oxygen will gain 2 because it's a -2 charge. So just keep in mind that you could potentially have a second electron affinity. You have to do it twice and add them together. But the first electron affinity, here's my symbol. It's delta H with a little 0. And then this one, since it's electron affinity, they use a lowercase e to indicate that that's the enthalpy we're talking about. And this one's the enthalpy change when 1 mole of electrons are added to 1 mole of gaseous atoms. Okay, and so if we look at the equation to kind of see what that looks like down here, here is the 1 mole of gaseous atoms. So we have 1 mole of chlorine atoms and they're in the gas state. And we add an electron to it. We give it an electron and we create a chloride ion that's still in the gas state. Okay. Now, this makes chlorine more stable because remember, nonmetals want to gain electrons to become stable. And so because we gave it an electron and we made it more stable, this is the first time that we don't have endothermic, we have exothermic. And so this one, it's a negative delta H. Okay, up till now, everything's been endothermic, but the electron affinity will always be exothermic. And then the last one on here is what we call the standard enthalpy change of formation. And this one, it's 0 and it has a lowercase f because we're forming a compound, okay? And this is the enthalpy change when 1 mole of a compound is formed from its elements in their standard states. So again, standard states means the naturally occurring state of the element. And notice that it has to be 1 mole of a compound. So that means in the equation, we can only have 1 mole on the product side. We cannot have a coefficient. And so sometimes that makes it like this, where I have to put a half in front of this chlorine to make it balanced. And the reason that we can do that for this equation, even though normally we say we don't want to have like fractions for balancing equations, is because the definition says we can only make 1 mole of whatever is here on the product side, the NaCl in this case, right over here. And so since we can only make 1 mole of that, the sodium is balanced, but the chlorine, because this chlorine in its standard state, it's diatomic. So we put the 1/2 in front of it in order to balance it, because if we do multiply 1/2 by this 2, that's 1, and then that matches the 1 chlorine that's over here on the product side. This one, if you notice, is exothermic, okay? They may not always be exothermic. Sometimes they're endothermic, but most of the time they're going to be exothermic. Because anytime you're forming a compound, typically that's going to be exothermic, because making that compound is making your elements more stable. It's making their atoms more stable. And typically that means that they're going to be at a lower enthalpy state. Okay. So all those definitions, the reason we talked about them is because now the next part is they're going to ask you to like construct what they call a Born-Haber cycle. And so when you go watch your videos on Canvas, they go through an exact example for how to do this. Okay. The only difference is the one in the video. I believe they do magnesium chloride, MgCl2, whereas your example, you're using NaCl. And so it says using the values given above. And so when they say values given above, they're talking about on this page we just went over. So all of these numbers that we just talked about. So like here's the 107, positive 107, that's endothermic, positive 496, that's endothermic, positive 242, that's endothermic, negative 349, that's exothermic, and negative 411, that's exothermic. So all of those numbers, those are the values that they're talking about you using to construct this cycle and you're calculating the lattice enthalpy. So notice it says that they want you to calculate delta H with the LAT. So they want you to calculate the lattice enthalpy, which is this definition we had all the way here up at the top. They want you to calculate the lattice enthalpy, and we can do that by using all of these other parts. It's kind of like a puzzle, and we put them together, and we figure out what the lattice enthalpy is, and we construct it on this diagram that looks like this. It's called a Born-Haber cycle. So when you're trying to work out this exercise on number 1, I want you to make sure that you have watched that video that's on Canvas that's recorded already, because like I said, there is an exact example. It just has magnesium chloride. So the only difference is that since yours is NaCl, you won't have, so like on magnesium has 2 ionization energies because it has to lose 2 electrons. Whereas for yours, for sodium only has 1. It just has the first ionization energy because it only loses 1 electron. That's pretty much the only difference, okay? The process for it is exactly the same. So this little diagram right here, you'll see in the video, he uses the same exact setup. The setup is always the same. The only difference is the numbers and the values you're filling in for each area. But the way that it goes together is the same. So that's kind of why I called it like a puzzle, because you're always going to put the pieces together, and then you put in the values, you put in the enthalpy values, and then there's an equation, and he goes through it in the video for how you add or subtract them together to figure out what the lattice enthalpy is. Okay. The second one, it's asking you to do the same thing. It says, using the values in the table below, construct a Born-Haber cycle and calculate the lattice enthalpy for calcium fluoride. So number 2 is asking you to do the same thing. I just didn't give you, this little diagram. So you'll have to kind of draw it yourself. You can do it on your own paper and stick it in here if you want, or however you want to do it. So you'll have to kind of draw your own diagram for the Born-Haber cycle, but you're doing the exact same thing. It's just they've given you all the numbers right here in the table. I want to point out, though, that notice there are 2 ionization energies because calcium is in group 2. So remember, all the ones in group 2, they'll always have 2 ionization energies because they have to lose 2 electrons. And so that's why it gives you 2 different ones on this one that you have to use. The other part of today is talking about some of the factors that affect lattice enthalpy. The charge on your ion, the ionic radius of the ion, both of those are things that affect it. So for example, it says here, ions with higher charge will have a stronger force of attraction and therefore a higher lattice enthalpy. So, you know, if I was comparing like these 2 that it has right here, MgO, well, Mg is 2 plus and O is 2 minus, right? NaCl, Na is just a plus 1 and Cl is a minus 1. So these are both higher, they're both 2s. And so that means that since they're higher, they have a stronger force of attraction. And so magnesium oxide would have higher lattice enthalpy than sodium chloride. And you would explain it by saying that magnesium and oxygen have higher charges and therefore a stronger force of attraction and therefore higher lattice enthalpy, holding them together. The other factor that can affect it that's on here is the ionic radius. So an increase in ionic radius decreases the attraction. So if you have a larger atomic radius, you're going to have less attraction. So smaller atomic radius will have more attraction because they're going to be closer together. And so, for example, here it gives us NaCl and it gives us KBr, and it says that NaCl has a higher lattice enthalpy, and that's because if you were to look on the periodic table, okay, sodium is here, it's in the third period, and potassium is below it, it's in the fourth period. And so potassium is going to have a larger atomic radius because it has a whole nother energy level. Same thing with the chlorine and the bromine. If you come all the way over to the other side, chlorine and bromine, chlorine's in also in period 3, bromine's in period 4. So K and Br both have larger atomic radii. And so since sodium and chlorine have smaller atomic radius, they're going to be attracted more and therefore have a higher lattice enthalpy. Okay. There's some practice questions in there. I'll let you go, you kind of work on those on your own because that's part of your assignment. Briefly, I just want to talk about this last part, which is the enthalpy of solution and hydration. This has to do with dissolving things in water. So when you see this symbol, delta H with the SOL, that stands for enthalpy of solution. And it's the enthalpy change when 1 mole of an ionic substance dissolves in water to give a solution of infinite dilution, okay? So we're talking about taking an ionic compound solid, you know, like salt, like sodium chloride, and dissolving it in water because there's some energy changes going in there. In order to dissolve something, there has to be some energy changes taking place in order to make that happen. And so just like with the Born-Haber cycle, we can calculate this as well. What you do is you look at what's called the enthalpy of hydration, which is delta H HYD. And so the enthalpy of hydration is when you have 1 mole of gaseous ions that dissolve in water. And so what you do is you look at your lattice enthalpy. So it's right down here, lattice enthalpy and your enthalpy of hydration. You add them together, and that gives you the enthalpy of solution. Because the lattice enthalpy is how much energy it takes to break them apart. And the hydration energy is how much it takes for them then to be surrounded by the water molecules, okay, and dissolved. So when you total those up, that gives you the total enthalpy of solution, okay? Dissolving, okay, there's 2 parts of it, like I said. That's kind of what this part's saying. The solid ionic compound is broken down into its gaseous ions. That's the lattice enthalpy definition. And then the gaseous ions are hydrated by water. That's the hydration enthalpy. And so, like I said, those 2 steps, when you add them together, that gives you the enthalpy of solution. And so you can use Hess's law and an energy cycle to do that. Because here is my basic equation. I just took solid sodium chloride and I dissolved it into sodium chloride solution. But really what's happening is that it's kind of 2 steps. The solid has to break into the ions, gaseous ions, and then the gaseous ions get surrounded by water molecules like in this picture right here. So that's why we can add those 2 individual steps together, the lattice enthalpy and the hydration enthalpy, to get the enthalpy of the whole solution process. And so if you're given values like that, you can use Hess's law to add them together. And that's kind of what it has here. It says calculate the enthalpy change of solution for sodium chloride. And so we add those 2 together. And so you can actually, in the video, he talks about that these enthalpy changes, they're all listed in the data booklet. And so you have them to refer to on your test. You just need to make sure that you know how to look them up. Okay. So all they did was they looked up the enthalpy values on the table, and then they added them together. Okay. So I'm going to go ahead and stop there because we are about to have to go to lunch in a few minutes, but hopefully between that and what you have on Canvas, make sure you watch those videos because they go into a little more detail differently than what I did. you can make sure that you're working on your practice questions because they're due Thursday night, the ones that are in the notes. And so we'll come back on Thursday and kind of discuss and see if anybody